Okay, so here are a couple of examples which are useful for us to try out. Okay, now the first thing is to understand how to do a periodic shift or a circular shift. Okay, so this is where the relationship between the DFT coefficients and the DFS coefficients become very important. So if you look at a signal which is given by, let us say, 5, 4, 3, 2, let's look at maybe 6 samples, starting with a value of 1, 2, 3, 4, 5, 6. Okay, so this is the sequence. So if you were to think of it, x of n is 6, 5, 4, 3, 2, 1. Okay, that is the sequence that we have. Okay, and the origin is at the point where it's equal to 6. Now, if I want to look at x tilde of n, notice the same set of 6 samples will get repeated. Okay, so that is what is happening. So let's write down x tilde of n. X tilde of n is 6, 5, 4, 3, 2, 1. I'm going to move this. I'm going to create a little bit of space. Say that this is the pattern that is coming continuously, and then you have 6, 5, 4, 3, 2, 1. Give it a different color, and then 6, 5, 4, 3, 2, 1, then dot dot dot. Okay, so this is okay, and the origin is here. So what we have done is x of n gets repeated multiple times, okay, up to infinity. So the relationship between x of n and x tilde of n should be very clear in your minds how this thing is happening. Now, if we want to perform the operation x tilde of n plus 2, okay, x tilde of n plus 2, what that means is that you are going to advance the signal by 2 units of time. Okay, this corresponds to the origin shifting over here. Okay, so basically 4 becoming the origin, then you have to the right 3, 2, 1. So if you now draw a boundary of 6 samples, okay, so start, let me use a different color. Okay, let me use red as the boundary. You will now have the following sequence. So basically this 6 and 5 went outside of the window 0 to n minus 1. What happened was from the corresponding periodic repetition, another 6 and 5 came into the picture. So now look at this particular sequence. What is x of n plus 2? The one period that is situated in the window, which is 4, 3, 2, 1, 6, 5. Okay, so advance operation for for x of n in the context of what we are talking about has to be a circular shift of the sequence, a circular shift of 2 units of time, advancing the operation. Those 2 samples show up at the other on the other side. So basically think of what would happen had you done an advance operation on the periodic signal, and then look at what is within the window of the periodic signal. So this is the final shifted or the circularly shifted sequence which has been shifted by 2 units of time. Now this is a useful example for you to keep in mind. because this will help us understand some of the operations that we will be doing. So let us now look at another example. This is a second example, example 2. This is example 1. Okay, example 2, I want to convolve x2 of m with delta of n minus 1. Basically, this is x1 of n. Okay, let me index it as n itself. x2 of n convolved with x1 of n, and x1 of n is equal to delta of n minus 1. It's a impulse signal that is occurring, unit impulse occurring at a sample value equal to 1. Okay. Now, what do you expect when you convolve a signal with a delta function which is at n equal to with delta n minus 1? What we expect normally to happen is the following. So let's look at what would have happened had you done it with the periodic signal. So x2 tilde of n convolved with delta of n minus 1 would have produced for us x2 tilde of n minus 1. Okay, all the samples would have shifted to the right, n minus 1. Okay, now that's exactly what will happen in this case also. But let us see how to look at it as a circular convolution, because not as a periodic operation, but as a circular convolution. Okay, keep x1 of m as is, because the operation that we are going to be doing is summation m is equal to 0 through n minus 1, x1 of m, x2 of n minus m modulo n. Okay, so the first thing that we are going to do is time reverse x2 of n in its current position. Okay, how do you represent this? We showed yesterday. So that if you had a sequence in this particular case 1, 2, 3, 4, 5, the sequence is 5, 4, 3, 2, 1. This is x2 of n. Okay, now x2 of minus n. Okay, basically we have to interpret all of these values in terms of the modulo representation. Minus n modulo n. Okay, want to take it as n is equal to 5, modulo 5, and so what we find is that when you have the 0 valued sample will remain as is, x of 0 same as x of minus 0, x of 1 will be the same as minus 1, which is the same as 5 minus 1, which is 4. So basically whatever was at the position 1, 2, 3, 4, that now comes as the position number 1. Okay, so 5, 1, because that is the sample that has now come in when you do the time reversal. Okay, and then comes 2, then comes 3, then comes 4. Okay, this is not surprising at all, because when you did the time reversal, if you were to look at the periodic signal, what does it look like? 5, 4, 3, 2. So basically 5, 4, 3, 2, 1. This is what would have happened, and this would have been the next period would have been the 5, 4, 3, 2, 1 again. So basically what you saw is just the one window when you can always go back to the periodic signal and then obtain the result that we are interested in. Okay, then you multiply the two together, x1 of m, and so what is the output? The output when you convolve for this expression, let's call this as x3 of n. So x3 of 0, you have a sample at n equal to 1, it's got a value equal to 1, so this sample is equal to 1, x3. Okay, x3 of 1, that means you have to shift to the right, and then basically corresponding get the corresponding value. This will be equal to 5. x3 of 2, this will be equal to 4. x3 of 3 will be equal to 3, and x3 of 4 will be equal to 2. So 5, 4, 3, 2, 1 was the sequence, original sequence. You shift it by 1, you get x3 of 1 is 5, 4, 3, 2. What happened to the first sample? Either you can think of it as a circular wraparound or as the periodic extension of the preceding copy of the signal. So basically, this is the output that we have. So what you have is x of 0 is 1, x of 1 is 5, x of 2, 3, 4. These are 4, 3, and 2. So this is the output. So basically, how to perform circular convolution. Okay, that is a extremely important aspect, and you must be very clear on how to do that and be able to capture that in a correct manner. Now, how would you have represented this circular convolution in a matrix form? Okay, we already discussed how to do this in matrix form. So let us do that. So here is the 5 by 5 matrix. This sequence is 0, 1, 0, 0, 0. That this is x1. Okay, so this corresponds to x1 of n. This should correspond to x2. Okay, so the sequence. So basically, we have to write it in the time reversed order. So the first sample is equal to 5. And remember, the sequence is now time reversed. What you have here is 1. Let me use a different color. 1, 2, 3, 4. Okay. So where is this coming from? 1, 2, 3, 4. That basically, that is the previous what was there before. That is what is being captured here. Okay, so this for the circular convolution, this has been brought here. Okay, next sample, you have 5. Okay, corresponding operation. This will become 4, and then you have 1, 2, 3. Then you have 3, 4, 5, and 1 and 2. And then 2, 3, 4, 5, and 1, and finally 1, 2, 3, 4, 5. Okay, so basically this will pick out the second column of the of this matrix as the output. So 1, 5, 4, 3, 2, 1, 5, 4, 3, 2 is the second column, because you are multiplying with a column vector with only one non-zero value, and you can verify it either through the numerical computation, you can verify it through periodic convolution, you can verify it, you can compute it using the matrix operation. All of those are perfectly okay, provided you are making it correctly. That's the most important aspect. Now, let me also highlight for you one more very important result, and with that we will then move on to the final topic of today, which is how to compute the linear convolution using the DFT. Now, here is example 3. This is example 3. Okay, we have a sequence x1 of n, a second sequence x2 of n. So we will take n equal to 6, and x1 of n has got length 6, x2 of n has got length 6, and we want to do a circular convolution of these two sequences, n-point circular convolution. Okay, so what will be the n-point circular convolution? If you look at it in the matrix form, again it will be 1, 1, 1, 1, 1 multiplied by a column vector which is 1, 1, 1, 1, 1, 1, and these are identical. Okay, so let me just use a different color. 1, 1, 1, 1, 1. There will be 6 ones. Okay, then we have 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, and finally, let's do this. Okay, what we get at the output is when you do the circular convolution, you will get the same length sequence. It will be 6, 6, 6, 6, 6, 6. Okay, notice that's what we get as the circular convolution. This n is equal to 6. All of them, and the height of the sequence is equal to 6. Now, how do we? How could you have done it using the DFT process? Because when we say that we want to do x1 of n convolved with n-point convolution with x2 of n, we know that this corresponds to the DFT coefficients x1 of k and x2 of k. Correct? Now, what I would like you to do is to verify what happens when you take D6, that's a 6-point DFT matrix, and multiply it with the following sequence. 1, 1, 1, 1, 1, 1. Okay, DFT 6 coefficients, and I would like you to verify that the following are the results. The first sample will be equal to 6. Remember, we said x of 0 is the sum of all the DFT, the input sequence. And interestingly, in this particular case, you will find the other 5 samples to be equal to 0. Okay. Now, is this a surprising result? The answer is no, because what you have in the time domain is a periodic signal which is of all of the same height. Okay. Now, think of what would have happened had you done a periodic extension. A periodic extension would have resulted in the next set of 6 samples also being equal to 1, next set of 6 being equal to 1. So, basically, you would have had a constant value of 1 at all instances of time. Okay. Now, that's a periodic signal. What is if the input signal is a constant in the time domain, what do you expect in the frequency domain? An impulse. And what you do, would you have gotten for the periodic of this signal? You would have seen a periodic, an impulse at time k equal to 0, k equal to 6, k equal to 12, a periodic signal. And if you are looking at only one period, you will see only one impulse, and that is what you are seeing. That is at time k equal to 0. What is the height of the impulse? It is equal to 6. So, if you were to ask you to write down that if x1 is equal to x2 equal to the following 1, 1, 1, 1, 1, 1. Okay, write down for me what is x1. You will find that this is the same as x2 equal to 6, 0, 0, 0, 0, 0. Okay. Now, if you were to multiply x1 of and x2, then what will you get? x1 multiplied by x2. This will be equal to 36, right? Basically, those two samples multiplying each other. 0, 0, 0, 0, 0. Okay. Now, is this something that is correct? How do we verify? If this is, let's call this as x3. Okay, then the corresponding time domain expression for x3 of n will be equal to 1 by 6 summation k equal to 0 through k minus 1 x3 of k. Okay, so what do you get? You will get x3 of n In all cases, x3 of 0 will be equal to 36, so 1 by 6 will be this. And therefore, regardless, multiplied by Wn minus Kn, okay, and you will find that x3 of n is equal to the value equal to 6 for all values of n equal to 1, 2, and that's exactly what we got. Okay, so important thing to note, how to do circular convolution in time, that is something that you should do, either using the matrix representation or during the graphical representation. You also now have seen how to do the circular convolution by going to the DFT domain and looking at it as a product of the DFT coefficients, and then the inverse DFT will produce for you the same result. Okay, so two important results that I want you to carry forward from here is the following. Okay, multiplication in time. Multiplication in time, that is a property of the DFT. Okay, so if I multiply two sequences of length n, x1 of n multiplied by x2 of n, then I get the DFT coefficients using a circular convolution, 1 over n x1 of k circular convolution of n samples x2 of k. Okay, you must be able to write down the expression. This is nothing but 1 over n summation m equal to 0 through n minus 1 x1 of m x2 of k minus m, but k minus m may go outside the range, so you take it as k minus m modulo n. So this is the endpoint circular convolution. This is multiplication in time. Okay, so multiplication in frequency. Multiplication in frequency. This is the other property that we have in the context of the DFT. What we say is that x1 of n, endpoint convolution with x2 of n, this is endpoint circular convolution, will have a DFT given by x1 of k multiplied by x2 of k. These are the two important properties, and they will come into play in many places and in many ways. So this is important for us to be able to capture and also to be able to apply. Okay. So now let me sort of introduce to you another aspect that I would like you to consider and also be able to apply. And so this is going to be maybe we look at some examples, and then we will look at how to apply these results. Okay. So first is maybe a couple of examples. Again, I always want you to be very thorough in terms of the understanding of the concepts. All right, so this is an example. I would like you to compute. We are given that x of k is the following: 1, 0, 1, 0. Okay, what is x of n? How would you do that? So then what we have is, we know that x is equal to d4 inverse times x. Okay, and d4 inverse, this is equal to 1 by n d4 conjugate times x. So let's write that down. So the vector x will be equal to a scale factor of 1 by 4 and then d4 conjugate 1, 1, 1, 1. They're all real valued. 1 w4 minus 1, w4 minus 2, w4 minus 3. That's the conjugate of the second row. Then you have 1 w4 minus 2, w4 minus 4 and w4 minus 6. and then finally 1 W4 minus 3, W4 minus 6 and W4 minus 9. I hope you are comfortable. This is the matrix that represents D4 conjugate. Okay, and we can look at the individual values. I would like you to go through and verify that this comes out to be the following matrix. And for this, you would have to substitute what W is, what the exponents are, and you should verify this comes out to be 1, 1, 1, 1. Okay, by the way, it will be this matrix multiplied by the corresponding xk's. So this will be 1, 0, 1, 0. That is what will be equal to. So this is equal to 1/4. Now this is what I want you to verify. It will come out to be 1 j minus 1 minus j. 1 minus 1, 1 minus 1. 1 minus j minus 1 j. Okay, again, very, very compact matrix. The inverse matrix turns out to be, in this case, this is the relationship. And then the column vector which contains the x comma k's, x of k's. 1, 0, 1, 0. So basically, you are combining column number 1 and column number 3 as the result of what you get. So if you do that, then what you get here will be 1/2. In this case, the next term both will cancel. Then you will get 1/2 and then you will get 0. Okay. So what we can say is the following: x of n, if it is 1/2, 0, 1/2, 0, the corresponding DFT coefficients are given by 1, 0, 1, 0. Okay, we may not have guessed it from looking at it, but go through the operation and be able to verify that. Okay,